In this lesson, we shall focus on mathematics, MATH141 calculus UKZN module. We shall look at techniques of integration, but also applications of integration to volumes and areas as follows. Right, there's something called the area formula. Right, so let's first talk about the area formula very briefly. If f and g are continuous functions on the enclosed interval AB, and if the function f of x is greater or equal to g of x, or it's above g, or at least equal to g for all x in AB, closed interval AB, then the area of the region bounded above by y equals f of x, below above is bounded by f of x, above is bounded by f of x, below is bounded by g of x on the left. On the left by the line x equals a, and on the right by the line x equals b. So yeah, that's what you have. On the left, right, and on the right, something of this nature. And if this happens, then the area obtained by actually performing the integration, performing the definite integral. Right, the area obtained by performing the definite integral, which is the definite, implies the integral with limits of integration from a to b. So you'll take the upper curve f of x minus the lower curve, or you can say right minus left, up minus bottom, whatever the language. Okay, let's look at an example quickly before we look at the third problems. Find the area of the region bounded above by y equals x plus 6, below by y equals x squared, right, and bounded on the sides by the lines x equals 0 and x equals 2. And what we have here is very, very easy, as follows. The y equals x squared curve is this one here from grade 10. Y equals, so this one is actually the curve y equals x squared. Then we have the curve, which is a line y equals x plus 6. Right, so when x is 0, y becomes 6. When y is 0, x becomes minus 6. Like so. So that y is x plus 6. Right, so, okay, you have exactly this here. Okay. Now at this point, we want to find the area of the region bounded by this. Right. So now it is actually the area of the region bounded above by the line. So this line is above, and below by the parabola. So the parabola is sort of below this way. Okay. Now, first things first, you need to determine the points of intersection. Right, the points of intersection. So let us find the points of intersection. Right, what are the points of intersection? To find the point of intersection, so we make x squared to be equal to x plus 6. This means that we have x squared minus x minus 6 equals 0. And then we have x minus 3, x plus 2 equals 0, giving us x equals 3 or x equals negative 2. Like so. What is then the area? The area, therefore, okay, at this point, first things first, let us find a bit more information. But yeah, you note that on the sides by the line, so yeah, there's x equal to 0, x equals 2. Let's just plot those lines also, because it's just limited to those. So you'd have, therefore, that at this point, this is the line x equals 0, the y-axis, and x equals 2. All right. Okay, so now x equals 0, x equals 2, like this. So then the area can be actually determined as, so now you have those points of intersection there. But obvious that these points, they are not so important, those points of intersection. Because you're able to see that at whenever x equals 2, y is 4. Whenever x equals 2, on the line, x equals 2, 2 plus 6 gives us 8. Right. And then you have 0, 0. So that the area, which is the integral, now you actually need to analyze this and say, if you look at this area here, you can look at it as between for the x-axis, or you can imagine an error that sort of, goes through the region and rises to the top. Now, when this happens here, maybe you can use a green color this way. And therefore, this means that you'll be dealing with the integral from 0 to 2. X equals 0 to x equals 2, the upper curve. We have x squared dx. So that you have x squared out of 2. 6x, x cubed out of 3. And then we have 2 squared out of 2. 6 times 2. 2 cubed out of 3. Minus 0. If you substitute, you get a 0. The 2 squared, it's 4. Out of 2, it's exactly a 2. 6 by 2 is 12. Minus 8 out of 3. 2 by 12 is 14. Minus 8 out of 3. And 3 by 14 is exactly 30 and 12. 42 minus 8 out of 3. Okay, subtract the 8. Remove the 6, you get a 34 out of 3. Right, so this is what exactly you get. 34 out of 3 units squared. Right, in which case, therefore, these points of intersection are not so significant for this question. We move to the next one. Next question. Find the area of the region that is enclosed by the curves y equals x squared and that. That is the same thing. Okay, find the area of the region that is, yeah, okay, so it's different because it is such that now you have more, it's exactly more general. So you do not have the other lines. Y equals x squared. Minus 6, 6. Okay, x plus 6. So now, okay, you want to find the area of this, but we have already got the points of intersection. What did you get the points of intersection to be? We got them to be 3 or minus 2. Right, so you got the points of intersection to be 3 minus 2. So whenever x is 3, y is 3 squared and 9. Whenever x is minus 2, y is a 4. Like this. Okay. And with this mentioned, therefore want to find the area. So the area. Right, so the area would be the integral. Now, if you want to integrate with respect to x, you realize that x is -2 here, and x is a 3 there. So I integrate from -2 to 3. And then we take the upper curve. If you imagine a line that passes through the region vertically in the direction of increasing y values, then the upper curve becomes a straight line. And then minus the lower curve, which is the parabola. All right, now upon careful examination of this, you find the integral. The integral of the x squared becomes x squared out of 2. X cubed out of 3. Area. Okay, let's find the area. Right, we just perform substitution. Yes, please.
Yes. So in cases like this, I think we took the integral between the interval of -2 and 3.
Yes, between the
Yes.
x coordinates, right? The -2
Yes.
is an x coordinate and 3 is also an x coordinate. Yep.
Yes. May I ask, when do you know that to separate the area? Because in some instances we cannot get the answer as you use that interval, but instead if you separate the area, we do get an answer. For example, like
Yes.
saying yeah, between -2 to 0 and then from 0 to 3.
Yeah, I
What
get
is
your
the
point.
difference?
What is the difference? Okay, good. So yeah, the difference would be that it really depends on how you look at it, because if this area can be separated, you know, because if you are to integrate from -2 for x and then to 3 for y, what you need to look for is if you draw a random line, this on the left of the y-axis and on the right of the y-axis, or anywhere within the region, will the line always actually penetrate the region through the same curve and exit through a curve with the same equation? So it's about equations. So now, if I draw this vertical line like on the left of the region, I can see that it's going to enter the region through the parabola. But even on the right, it's going to enter through the parabola. Even if I can draw a vertical line here, it's going to enter through the parabola. It means, therefore, the lower curve, if I integrate from -2 to 3, the lower curve is just a parabola everywhere. And the upper curve through which these lines I'm drawing exit, the upper curve is the straight line. Now, if somebody would look at the curve horizontally, then there's an issue with that. Because if you draw like this line here will actually, now if you do the right minus left, you'd see that right is the parabola, but left for this line here, it's this straight line. But below this point of intersection, right is the parabola, on the right is the parabola, but on the left is the parabola again. Meaning that if you integrate with respect to y, you need two areas. You would need one area above and one area below if you integrate with respect to the y-axis. So you need to draw some random lines to see if the lower curve and the upper curve, it's the same curve throughout the region. I'm sure we shall do a couple of examples on this. Okay, even this one, we can do two areas for this one. Okay, but there are times when, so you don't just split. We are forced by the situation to split the areas. But obviously, if you look at, if you integrate from -2 to 3, then the bottom curve is only one. It's only this one. And therefore, the upper curve is only the straight line. Okay, yeah, we're going to split at some point.
So,
Yes, please.
so basically what you mean is that whenever my upper curve between the two curves, basically between the two curves, whenever the other one is in the negative y-axis, and then the other one is in the positive y-axis, then I have to use that for to understand.
Yeah, definitely. Then you might actually obviously you know, sort of partition the total area into two areas, you know. But we're gonna just do that now quickly. Okay, right. So now this the upper limit is 3 and the lower limit is -2. So you're gonna have 3 squared out of 2, 6, 3. Okay, and then minus 3 cubed out of 3 minus. Then you plug in -2 here. You have -2 squared out of 2. Then you have 6 minus 2. And then you have -2 cubed out of 3, like this. And therefore, you can be able to find the area. Okay, you can be able to find the area. Now, 3 squared is a 9 out of 2. 6 by 3 is 18 minus... Okay, 3 cubed is 27. Divided by 3 is a 9 minus... Okay, minus 2 squared is a 4. You divide by 2, it's a 2 plus 12. Okay, so this is plus. And then negative by negative is what? Okay, so this is minus. But negative times negative 12 is a plus 12. Negative by negative, it's plus. You cube the -2, you get -8 out of 3. Right, so now let us check this out. So what you're getting is 9 out of 2. 18 minus 9, it's a 9. 9 minus 2 is a 7. Plus 12, it's a 19. Minus 8 out of 3. 6. 6 divided by 2 is actually 3 by 9, 27 plus 6 times 19 minus 6 divided by 3 is a 2 by 8, 16. Right, so you have exactly that one. And so now you can just use a calculator if you want, just to save time. Right, so using a calculator, so if you have 27 plus 6 times 19 minus 16 out of 6. All right, and then, okay, that's fine. Okay, that's okay. If in case yeah, it's 125 divided by 6. So this is 125 divided by 6. It is units squared. All right. So this will be exactly the, if we integrate with respect to x, that is going to be the area. But you see, as you asked now, we can do it differently. We can say there's this one here, the parabola, and then we have the straight line like this. So this is the area. And then now, if you have here the points of intersection were 3 minus 2, 4 and 9, y, and then x plus 6. Okay, so yeah. Now let us look at it this way. Now you ask the question. So now if we're to integrate respect to y, then, for example, a horizontal line that is going to penetrate the region like this, it's going to reach the region first on this straight line and then exit through the parabola. But a horizontal line that is going to go through here is going to enter through the parabola and exit through the parabola, meaning that at this point we need two areas. So we need area 2, but also would need area 1. Okay? Okay, yeah. Area 2, area 1. area. Right, so now the area, if we integrate with respect to y, the answer is going to be the same. But the area is going to be like area 1, area 2. Because now the horizontal lines, as I said, the horizontal line here enters this region. It looks like one region, but enters the region through the line that is slanted like this and exits through the parabola. Right, so which means therefore you're going to have the fact that at this point you would have to integrate. Right now you want to integrate respect to y, so you integrate respect to what y is here and what y is there, because y therefore runs from whatever y is at this point of intersection to whatever y is at that point. So y is 4 and then y is 9. Now with these mentions, you have y equals x squared, y equals x plus 6. So that at this point, then, you have x is y minus 6. So that now you're going to actually look at this, but also whenever this parabola y is equal to x squared, it means x is plus or minus the square root of y. Okay, so this parabola has x equals to the square root of y this side, and there's also x equals negative the square root of y this side. Okay, let me take a question. Okay, I'm checking your question. Okay. Okay, that's fine. Okay, you're suggesting that you'd not have a problem with area problems, so we can just skip so that we don't waste time on the right. So I don't waste time on area. I was just confused about the area. You separate the graph and where you don't. Okay, that's fine. Thank you. That's okay. So let's move on. Right, because obviously now I want us to look at these areas. Okay, we're going to come back to the areas. I want us to spend time on the other things. I want us to look at the volumes. Then we can do some of the exercises, you know, because I'm trying to make sure that at least we answer your questions. Okay, now there are volumes by slicing discs and washers. Let us discuss the volumes by slicing discs and washers. Right, in the last section, we showed that the area of a plane region bounded by two curves can be obtained by integrating the length of a general cross-section over an approximate interval. In this section, we'll see that the same basic principle can be used to find volumes of certain three-dimensional solids. Volumes by slicing. Recall that the underlying principle for finding the area of a plane region is to divide the region into thin strips. Approximate the area of each strip by the area of a rectangle. Add the approximations to form a Riemann sum, and take the limit of the Riemann sums to produce an integral for the area. Under appropriate conditions, the same strategy can be used to find the volume of a solid. Right, the idea is to divide the solid into thin slabs. Approximate the volume of each slab. Add the approximations to form a Riemann sum, and take the limit of the Riemann sums to produce an integral for the volume. Right, so you have the thin slabs. Thin slab for the sphere cut into horizontal slabs. This is sphere and cut into horizontal slabs. A right pyramid cut into horizontal slabs. A right circular cone cut into horizontal slabs. Right circular cone cut into vertical slabs. Okay, let's see what we need to do here. Okay, we have the formulas that we're going to learn, like formulas 3 and 4. Let S be a solid bounded by two parallel planes perpendicular to the x-axis at x equals 8, x equals b. If for each x in AB, the cross-sectional area of S perpendicular to the x-axis is A of x, then the volume of the solid is what? Right, the volume of the solid is V equals the integral from a to b a of x dx, provided a of x is integrable. Provided a of x is integrable. So we repeat, let S be a solid bounded by two parallel planes perpendicular to the x-axis, x equals a at x equals a, and x equals b. If for each x in AB, the cross-sectional area of S perpendicular to the x-axis is a of x, then the volume of the solid is given by this, provided a of x is integrable. There is a similar result for cross-sections perpendicular to the y-axis, right? So let S be a solid bounded by two parallel planes perpendicular to the y-axis at y equals c and y equals d. If for each y in the closed interval, the cross-sectional area of S perpendicular to the y-axis is a of y, then the volume of the solid is V equals the integral from c to d a of y dy, provided a of y is integrable. Okay, let us continue. Right, so now we can actually quickly, without wasting much time, do some volumes here. Right, so let us find this volume. Derive the formula for the volume. Derive the formula for the volume of a right pyramid whose altitude is h and whose base is a square with sides of length a. Okay, with sides of length a. Right, at this point then, we actually are interested in finding the actual area. Right. So now, we know that the area okay, let's first describe this one here and say the area. Right, the area. Right, the area of the cross section. That y is a of y. Right, so now, if you look at the fact that the area of the cross section is given by what? Right, if now we actually are able to extract this cross section, if S denotes the side of a square, then the area would be given by the area of a square is side squared. Now, obviously, we're asking the question in terms of what the sides of the square, for instance, become exactly. Right, so now we will note the following. Let's first say at any, okay, this one is not really a particular example. It's not a very good example, but we can discuss it. Right, at any y, right, in the interval, at any y in the interval 0 to h, okay, that's fine. Yes, we shall do the arc lengths after this. Okay, so this one is just a very brief example. Right, so at any y in the interval 0 to h, Right, on the y-axis, the cross section. The cross section perpendicular to the y-axis is a square. If S denotes the length of a side, of this square, then by similar triangles, right, then by similar triangles, we can actually be in a position to obtain the following. Right, by similar triangles, we're able to obtain that, for instance, 1/2 S divided by 1/2 A. Right, so we take 1/2 S divided by 1/2 A is actually equal to H minus Y divided by H. H minus Y divided by H, like that. Okay, so this is one is a high school thing, but yeah, normally it won't be. It's not making S the subject to be A over H minus Y. Okay, I'm trying to conclude this because it's not so thus the area A of Y of the cross section at Y which is equal to A squared over H squared. So the volume. The volume becomes the integral from 0 to H. Right, so now we're integrating with respect to Y, so the volume becomes A of Y dy. Right, so the volume therefore becomes the integral from 0 to H, and you take A of Y dy. The integral from 0 to H, A of Y is exactly this, which is the side squared for the area of the area of a side, the area of a square. Right now, the area is this one. Dy. 0 to H. H minus Y. Right. So now you have the integral H minus Y squared dy. Right. Now we integrate this one here. So this is a squared over h squared. Okay, the negative is going to come out when we integrate this one. But because of the 2, we're going to divide by 2 plus 1, giving us a 3. H minus y, 3 from 0 to h. Just doing this one is not a typical sort of problem you'll find. And now, in the end, you actually can have a squared over h squared, which is the volume. Okay, let's just continue. It's a squared over h squared. So you continue 0 plus h cubed out of 3. If you substitute, it's going to be h cubed out of 3. And this is 1/3 a squared h. 1/3 a squared h. All right, so obviously you can see the distance from here to here is half a, and the distance from here to there is another half a. So that in the end, then the area of a right pyramid is 1/3 area of base is a squared by the height h. All right, so we have that. We continue to the next kind of questions, which are very important. Okay, let's look at solids of revolution. Right. Now, discussing the idea of solids of revolution, for example, we have the following. So a solid of revolution is a solid that is generated by revolving a plane region about a line that lies in the same plane as the region. The line is called the axis of revolution. Many familiar solids are of this type. Figure 5.2.8. We can take a line segment and revolve it. We can take a semicircle and revolve it about the horizontal axis. We can take this particular right angle triangle and revolve it. We get a solid cone. Here we get a solid sphere. Here we get a right circular cylinder. And if we take a component here and revolve it like that, we're able to get a hollowed right circular cylinder. And now we get to the hollowed right circular cylinders are of great interest to us. We discussed the volumes by disks perpendicular to the x-axis. We'll be interested in the following general problem. Right, the problem is that we let f of x be continuous and non-negative on the closed interval AB, and let R be the region that is bounded by y equals f of x below the x-axis and on the sides by the lines x equals a and x equals b. Right, and we have the x equals a here and x equals b. The problem is to find the volume of the solid of revolution that is generated by revolving the region R about the x-axis. Right, we have this region R, want to revolve it about the x-axis, and if we do, we get this particular shape there. Okay, good. But obviously it is from A to B, and we have still our A and B. Right, so if we revolve it about the x-axis in this direction, we actually therefore have that precisely, and we move forward. We can solve this problem by slicing. For this purpose, observe that the cross-section of the solid taken perpendicular to the x-axis at the point x is the perpendicular disk of radius f of x. Figure 5.2.9b. The area of this region is a of x, which is pi f of x squared. A of x is pi f of x squared. Thus, from 3, the volume of the solid is the integral from a to b pi f of x squared dx. Because the cross sections are disc shaped, the application of this formula is called the method of discs. Right, so with the method of discs, the volume will only have pi, the function squared. Let us do an example before we look at the charts. Let's just do an example before we look at the task. Find the volume of the solid that is obtained when the region under the curve y equals the square root of x over the interval 1 to 4 is revolved about the x-axis. Okay, we revolve this one about the x-axis. Let us find the volume. So the volume is the integral from a to b pi f of x squared dx. Volume is therefore the integral from 1 to 4 pi y equals f of x is the square root of that dx. One to 4 pi x dx. So now pi x squared out of 2. Okay, let's find the integral of this. So we use the formula here, but again we use the method of disks. So now if you integrate, it's pi, the integral of x, because x is to the power 1, it's going to be x squared out of 2 from 1 to 4. Pi out of 2, 4 squared minus 1 squared. What is 4 squared? It's 16 minus 1, 15. 15 pi out of 2. All right, so this becomes therefore the volume in cubic units. Cubic units. Right, so we have exactly that one. But first, as said, we first find the area, and the area is obtained as follows. And you realize that the area is pi times the f of x. So the f of x is sort of the radius. It's like pi radius squared, like the area of a circle. And this is called the method of disks that uses the disks, and each disk can be perceived as a circle. Now let's move on to the next question. Right, derive the formula of the volume of a sphere of radius r. Right, so we know that a sphere is this one. This is a circle of the equation x squared plus y squared equals the radius squared. Right. Now, the upper half of this is y equals the square root of r squared minus x squared. The volume, pi. A to b pi f of x dx. Okay. And therefore, what is the volume? Pi. Now, this one, the volume is going to be from x equals minus r to x equals r. Minus r to r, pi. What is f of x? It is exactly the square root of r squared minus x squared. Squared dx. Pi. Oh, okay. You see, there's a single pi. Only one pi is there. There's not two of them. Okay. Okay, you know that obviously we put the function. So the function f of x here is pi. Right? So we need to find the volume for the formula for the volume of a sphere of radius r. But if you revolve these about the x-axis, what are you going to have? Right, so you're going to have, you need to draw a line perpendicular to the x-axis because you are revolving about the x-axis. And if you revolve about the x-axis, you need to realize that this is going to create, it's going to create a circle. It's going to create a circle, and therefore this circle has its own radius. The radius is the distance from here to there. which is f of x. So which is the integral. Okay, now you square this. Okay, which is r squared. R squared minus x squared. Which is r squared x. Okay. Volume is pi. You put the r there, it becomes r cubed. Minus r cubed out of 3. You put the upper r. Minus, you put this r here, it's going to be minus r cubed. And you put the minus here. Then it's going to be plus r cubed out of 3. Right, so now, okay, so now you have the r cubed minus r cubed out of 3 to r cubed out of 3. Okay, so now you have minus 3r cubed plus that, which is minus 2r cubed, which is plus 2r cubed out of 3. Okay, you can add those numbers. It's okay. I know you can do that. So that in the end, then you add everything. So 2r cubed is 4. Pi r cubed out of 3. Right, and therefore this one, it's the volume of a sphere of radius r. Okay, make sure you understand this, because once you understand this, then you can be able to do the method of the disks. Right, the method of disks. You can be able to use the method of disks to find volume, but they don't like it most of the time. I think that what I've seen is they like the shells, and we're moving to the shells. Right, now, for instance, now the volumes by washers perpendicular to the x-axis. Not all solids of revolution have solid interiors. Okay, some have holes or channels that create interior surfaces, as in figure 5.2.8. Right, if there's a hole inside, like here, there can always be a hole, even if, okay, if this is the region, but if you revolve this, there's a space here, and therefore, because of this space, then this space is going to create a hole. Right, so we'll also be interested in problems of the following type. Now, if you look at the problem in 5.2.5, the problem is, you let f and g be continuous and non-negative on AB, and suppose that f of x is greater or equal to g of x for all x in the closed interval AB. You let R be the region that is bounded above by y equals f of x, below by y equals g of x, and on the sides by the lines x equals a, x equals b. Find the volume of the solid of revolution that is generated by revolving the region R about the x-axis. We can solve this problem by slicing. And slice the region. For this purpose, observe that the section of the solid taken perpendicular to the x-axis at the point X is the annular or washer-shaped region with inner radius g of x and outer radius f of x. Its area is a of x, which is pi f of x squared minus pi g of x squared. So here, even here, you take the area of the upper curve minus the area of the lower section, right? And then now you have pi where the f is the upper one and g is the bottom one. That's from 3, the volume of the solid becomes exactly this. Because the cross sections are washer shaped, these are like washers. There's a hole inside, and then there is something like donuts. Washer shaped like that. The application of this formula is called the method of washers. Method of washers. So the method of washers is the two curves like this, and then you take the upper curve minus the upper curve squared minus the lower curve squared, but you're still integrating from A to B. Where A is this one here and B is that one there. We move forward. Okay, let us just do an example on the method of washers so that we quickly move to the other methods as well of finding the volume. Now, find the volume of the solid generated when the region between the graphs of the equations f of x equals 1/2 plus x squared and g of x equals x over the interval 0 to 2 is revolved about the x-axis. So now let us do this one. Right, so let us sketch this quickly. So to have a rough idea of what's happening. So you have the y-axis and the x-axis like this. So now the graph of f of x equals 1/2 plus x squared. Right, so when x is 0, then y is actually 1/2. So it will be the parabola that's just lifted up a little bit. Is the parabola that's lifted by 1/2 units, so that when x is 0 here, our parabola is 1/2 plus x squared. Okay, 1/2 plus x squared. Okay, the parabola is lifted like this, so that you have 1/2 here. All right. Check. Okay, check this out. Then we have g of x. And what is g of x? G of x is the straight line that actually is going to cut like this. So it is actually exactly g of x equals x, which is 1/2 plus x squared. Okay, so you integrate like that. Okay. Now, what is the volume? Okay, but note that this one is from 0 to 2. So 0 to 2. Okay, at 2, then this point, for instance, is what? This point is x is 2, y is 2, because it's like y equals x, y equals x. This one, x is 2, and then y is what? It's 4.5. 4.5, which is exactly 9 out of 2. 9 out of 2. Then the volume. The volume becomes the integral from a to b pi f of x minus g of x dx squared squared. Can write it nicely. Okay, you revolve this one about the x-axis, and if you do revolve it about the x-axis, you're gonna revolve it like this, just like that. And when you do, you're able to get some interesting stuff. Just want to write clearly here. Okay, then let us find the volume. As I said already, so if this is revolved about the x-axis, what then you're gonna have is that we have pi f of x minus g of x dx. And then now you have the integral from 0 to 2 pi. Okay, then you have, okay, so if you do the same now, which one is the upper calf? It's the f, and then the bottom one is g. So which means that you're gonna have 1/2 plus x squared. You square it. The g of x is this one, and you square that, and you get a dx like this. Right. And let us check this out. So you do the volume, which is the integral from 0 to 2, from x equals 0 to 2 pi. You square this one, it becomes exactly 1/4 x squared x to the 4th power minus x squared dx. It is the integral. Pi. X squared cancels. 1/4 plus x to the 4th power dx. Right, so if you integrate this one now, the integral of the 1/4 is x out of 4, x to the 5th power out of 5, from 0 to 2, which is pi, 2 out of 4, 2 to the power 5 out of 5. Which is exactly this one. So let us check this out together. So it tells us that the volume is pi 1/2 plus. So it becomes exactly 1/2 plus. Let's check it out. 2 to the 5 is 32 out of 5. Okay, let's put 10. Divide by 2, get a 5. Divide by 10, you get a 2, giving us a 64. And this one is 69 out of 10. Okay, so the answer is exactly that. So you can even say the answer is 69 pi divided by 10 units cubed. That would be the volume. And this volume has been determined by actually the method of washers. Method of washers. What you call the washer method. Let's move on to the next question. Okay, now the volumes by disks and washers perpendicular to the y-axis. Okay, they can also be perpendicular to the y-axis. Let's just take a look at that one. So the method of disks and washers have analogs for regions that are revolved about the y-axis, figure 5.2.14 and 5.2.15. Using the method of slicing and formula 4, you should be able to deduce the following formulas for the volumes of solids in the figures, for the method of the disks and the method of washers. Right. With obviously the disks themselves are here. So now if you have this one that is stuck on the y-axis, then you can use the method of disks because it is attached to the y-axis here, and you can start revolving it exactly this way, and then you're able to get this particular region. But now the method of washers, because there's a gap here and you decide to revolve it about the y-axis, then there's going to be a washer that is going to be actually like a donut, and because of the space there. Okay, and the formula therefore will become pi a function of y squared minus a function of y. But you see, it's pi a function of y squared, where this w is like the right minus left rule applies. And even here is like the right minus left rule, but just that right is u of y squared, and then left is the x equal to something. What is the x equal to? The x is equal to 0 on the y-axis. Okay, let's look at some examples. Now, I want us to find the volume. Right, find the volume of the solid generated when the region enclosed by y equals the square root of x, y equals 2, and x equals 0, which is x equals 0, are revolved about the y-axis, like that. Okay, if you do that, then you get exactly this here. And this one here is very, very clear, because you are able to take a look at these and understand. And this method here that is very, very useful here, because you can see that whatever you have here, it's nothing other than a disk. So the volume. Right, so the volume now from C to D. Right, and then now if you check very carefully, you would have pi, and then the formula is u of y, as we've seen it, squared dy. Right, so now for the y, you integrate from 0 to 2 for the y. So now you integrate from 0 to 2, that is integration. And then you have the pi, and then you use the right minus left rule. Right minus left rule. But now this is the function you have here. If y equals the square root of x, then x is exactly y squared. X is y squared. And then you put y squared, and then you square this. All right, and then you put dy like this. And you have the integral from 0 to 2, pi y to the 4th power dy. Performing the integral, you'd have the following. Right, you'd have the following. Okay, so we're good. We're so good. Okay, we are going on right now. And what do we get out of this? We get pi y to the 5th power out of 5 from 0 to 2. Right, so what are we able to achieve out of this? Would have exactly the following. To have exactly the following. Can you continue? So if you put in the 5, it becomes pi 2 to the power 5 of 5. 32 pi out of 5. Right. So we continue. We continue. So yeah, that is exactly what we have. Right. But now this one is the method of the disks. Method of disks. Right. Now let us see the next thing we're gonna do here. Okay, so we continue quickly. We continue with the next question. Continuing with the next question, we have exactly the following notion and concept as follows. Okay, there are other axes of revolution that become involved. Okay, I also shall look at this in the task. It is possible to use the method of disks and method of washers, washers to find the volume of a solid of revolution whose axis of revolution is a line other than one of the coordinate axes. Instead of developing a new formula for each situation, we will appeal to formulas 3 and 4 and integrate an appropriate cross-sectional area to find the volume. Find the volume of the solid generated when the region under the curve y equals x squared over the interval 0 to 2 is rotated about the line y equals minus 1. Let's take a look at this one. So now to actually do this, but very, very carefully, we're going to have exactly the following concept. First things first, we want to find the volume of the solid of revolution generated in this case. So you have to sketch our y-axis, this one, and our x-axis there. Right, so you'd have the y equals x squared, for example. So you have the graph of y equals x squared, y equals minus 1. It's at the bottom. And now find the volume of the solid that is generated by revolving the region under the curve over the interval from 0 to 2. Right, so from 0 to 2, the region under the curve is this one. Right, so now then you need to find the volume. What is the volume? The volume, therefore, is from 0 to 2. A of x dx. Okay, 0 to 2. And then we integrate from 0 to 2. Now, we want to actually, therefore, do the same and then say, we find precisely the area. The area is pi. Then we're going to do the upper curve. Upper curve. So if you revolve this one and you revolve it like this, what is the upper curve? The upper curve is actually the x squared graph. But now you need to find, because it is revolved about this horizontal axis, you therefore see that the upper curve is the x squared. And then you must find the distance between the upper curve and the axis of revolution. Right, because you need to find the volume of the solid generated when the region under the curve y equals x squared over the interval from 0 to 2 is rotated about the line y equals x, so that you have exactly the following. You have x squared plus 1, which is the distance between y equals x squared and this particular axis of rotation. Right? And then you minus, so it is squared, this one here, minus exactly 1 squared dx. Take a look at this. So now what we do here, first sketch the region and the axis of revolution. Right. Then imagine revolving the region about the x-axis. At each x in the interval from 0 to 2, the cross-section of the solid perpendicular to the axis y equals -1 is a washer with the outer radius x squared plus 1. Right. And inner radius 1. Right. So let us reason these very, very carefully. Right, so now if you revolve this particular region about the line y equals -1, you would realize, therefore, that you'd have to find a radius. I want us to pause and reason this carefully, and then we shall move on. You have to find a radius. So now if you revolve about this, you'd have something like this, and then you'd have something like this. Right, so, and when that happens, the question becomes, what is the radius? Right, so the radius now for the outer radius is going to be exactly x squared plus 1 squared. The inner radius is going to be the distance from here to there for the inner one, which is exactly 1 unit. That's why you have this. Let's continue. Therefore, the volume. Therefore, the volume is given by 0 to 2 pi. Okay, if you square this one, x to the 4th power 2x squared plus 1 minus 1 dx. 0 to 2 pi. Okay. Right, so okay, so you have 0 to pi, that x to the 4th power plus 2x squared. The 1 minus 1 is 0 dx. We find the integral. So you have pi x to the 5th power, 2x cubed out of 3, 0 to 2. 2 out of 5 out of 2. Okay, let's complete it here. Let's just complete the simplification. And then you have pi 2 out of 5, okay? out of 5 plus 2 out of 2 cubed out of 3 minus 0. Okay, now 2 to the power 5 is a 32 out of 5 plus 2 to the 3 is 8 by 2, 16 out of 3. Right. And therefore, this would give us exactly a 15. A 15. So, yeah, 15 divided by 5, giving us exactly a 3. And 3 by 32 is a 96. 15 divided by 3 is a 5. By that gives us exactly 80. And this is 176 pi. Pi divided by 15, like this. Right, so now this is exactly the washer method. So we're able to get a washer by revolving this, the outer radius, and then we actually deal also with the inner radius there. Okay, we move forward. We move forward. Find the volume of the solid generated when the region enclosed by that is revolved about the y-axis. Take a look. Take exactly a good look. Right, we take exactly a good look. Uh-huh. Okay, this one we've already done. Okay, this one is solved already. It's solved already. We solved it before, wondering why I put it here, because this one is example 6 and this one is 5. So we solved it earlier. Okay, let's look at the cylindrical shells, volumes by cylindrical shells. Right, I think this is sort of the burning issue. Most of your TOT questions are on the cylindrical shells. Let us spend a few minutes and then we go to the TOT quickly. Right, the methods for computing volumes that have been discussed so far depend on our ability to compute the cross-sectional area of the solid and to integrate that area across the solid. In this section, we will develop another method for finding volumes that may be applicable when the cross-sectional area cannot be found or the integration is too difficult, the cylindrical shells. In this section, we will be interested in the following problem. We'll be interested in the following problem. Let's check. Right, so once again, in this section, we'll be interested in the following problem. What is the problem that we are trying to solve here? Right, we are trying to deal with, if you let F become be the continuous non-negative, be continuous non-negative on the closed interval AB, and let, okay, yeah, closed interval AB, but this is supposed to be this way, please. Author of the book, this is just a typo in the book. Let R be the region that is bounded above by y equals f of x. Y equals f of x is above, below by the x-axis. The x-axis is below. And on the sides by x equals a, and x equals b. Find the volume of the solid of revolution S that is generated by revolving the region R about the y-axis. We can revolve this one about the y-axis, like this, about the y-axis. Right. Sometimes problems of the above type can be solved by method of disks or washers perpendicular to the y-axis. But when that method is not applicable or the resulting integral is difficult, the method of cylindrical shells, which we will discuss here, will often work. When the things are difficult, then we use the cylindrical shells. The cylindrical shell is a solid. What is a cylindrical shell? A cylindrical shell, by definition, is a solid enclosed by two concentric right circular cylinders. Right, figure 5.3.2. The volume of a cylindrical shell with inner radius R1 and outer radius R2. Inner radius R1 and outer radius R2. Okay. Okay, continue. Right. Inner radius R1 and then outer radius R2. And this is shell. It's a solid enclosed by two concentric right circular cylinders, like that. The volume V of a cylindrical shell with inner radius R1 and outer radius R2. Okay, let's look at the formula. Volume by cylindrical shells about the y-axis. Let F be continuous and non-negative on AB, right? And let R be the region that is bounded above by f of x and below by the x-axis. We saw that. And on the sides by x equals a, x equals b. We just saw the diagram. Then the volume V of the solid of revolution that is generated by revolving the region about the y-axis is the volume, which is equal to the integral from a to b 2 pi x f of x dx. V equals the integral from a to b 2 pi x f of x dx. Okay, let's move on. We can see the formula. Right, but you know that it is 2 pi x f of x dx. Okay, let us use the method of cylindrical shells and then we go to the task quickly. Right, for example, in this particular example here, we have a very simple exercise to do, a simple example to do. Use cylindrical shells to find the volume of the solid generated when the region enclosed between y equals the square root of x equals 1, and x equals 4, and the x-axis is revolved about the x-axis. Right, so let us have a rough idea of the sketch. Right, so you'd have y equals the square root of x, y, and then x. So you have 1 to 4. And then this is actually what we have here. Right. And now, if this is the case, we want to actually use cylindrical shells to find the volume of the solid generated when the region enclosed between that, square root of x equals 1, x equals 4, and the x-axis is revolved about the y-axis. So the volume formula is this one. Right, so now if you look at the y-axis, right, as we said already, if it is revolved about the y-axis, you'll have dx. And the limits of integration, you are revolving it about the y-axis, but you put the limits of integration from a to b, etc. So you're going to have the integral from a to b 2 pi x f of x dx. This is the integral from 1 to 4 on the x. Okay. What is f of x? This is the square root of x dx. Right, so now this is the volume. Which is 2 pi 1 to 4, then you have x to the power 3 over 2 dx. Right, so, which is 2 pi, the integral of, you add 1 here, which becomes exactly 2 out of 5, x to the power 5 out of 2, then the integral from 1 to 4. So now you multiply 2 by 2, which is a 4 pi, which is a 4 pi, then you substitute the 4 here. 4 to the power 5 out of 2, then substitute a 1. Right, and therefore this is exactly what? 4 pi out of 5, and then this is 4, it's 2 out of 2, but then there's 5 out of 2 minus 1. 4 pi out of 5, and then the 2 cancels, giving us 2 to the 5 minus 1. 2 to the 5 is 32, minus 1, which is 31. 4 pi out of 5, 31. Right, so that the volume, 4 pi that, which is 62, then, yeah, 4 pi 30, it's 120, so it's 124. 124 out of 5. Units, can I say cubic units? Cubic units. So now we've been able to find the volume, right, formed such that x is between 1 and 4. And as indicated here, you have that then the volume of a solid of revolution that is generated by revolving the region R. What is the region R? Let F be continuous non-negative from A to B. Let R be the region that is bounded above by y equals f of x and below by the x-axis. Okay, so this is the method of the cylindrical shells. Let's check. Next question. Okay, I want us to discuss one example and then we go quickly to the charts. Now, for example, use cylindrical shells to find the volume of the solid generated when the region are in the first quadrant and closed by this. Let us deal with that in the first quadrant. In the first quadrant. So you're going to have, for example, this one. Take a look at this one. And then you have y together with x. Then the first enclosed by y equals x and y equals x squared. Right, so you would have, yeah, but it is in the first quadrant. So you can look at y equals x squared like this, and then you have also the line y equals x like this, and then they meet. So x squared, y equals x. X equals x squared. X minus 1. X 0, x is 1. Okay, let us do that. So here is the point of intersection is 0 and 0. And then here, when x is 1, y is 1. And when x is 0, y is 0. So the points of intersection are 0 and 0. And we have exactly this here. Right, move forward. Now, let us find this here. The volume. Use cylindrical shells to find the volume. Okay. Right, so cylindrical shells will be, now you integrate, oops, this is up to 1 and 1, my goodness, okay, so it is exactly up to 1 and 1. You'd have to, therefore, by cylindrical shells, you integrate from A to B, 2 pi x f of x dx, which you integrate from 0 to 1, then you have exactly 2 pi x. Right, what is f of x? Right, so you need to analyze this very carefully and realize that at this point, at this juncture, by the method of the cylindrical shells, you're going to have exactly what? If this is revolved by about the y-axis, we're going to use the right minus left rule. We're going to use the right minus left rule. What is the right minus left rule? Once again, yeah, you're going to have the recording. So I realize that maybe you got disconnected there. Okay, right. You're going to, because now you revolve about the y-axis. So if you revolve about the y-axis, you have exactly the following. Take a look. You revolve about the y-axis, and if you do so, you'll use the right minus left rule that you know so well. Right. Okay, yeah. Wondering why the disconnection, you'll forgive me. I think it might just be the network. It might just be the network. that you are partly disconnected there. Right, that you are partly disconnected there. Okay, now as illustrated in this particular diagram, at each x in the interval from 0 to 1, the cross section R, if the region R, this is the region R, parallel to the y-axis, it generates a cylindrical surface of height what? What is the height of the cylindrical surface? First, we need to find the height of the cylindrical surface. We are able to see that the height of the cylindrical surface is exactly what? It's exactly the top x minus the bottom, x squared. So this is the height. This is the height. Top minus bottom, which is, what is the top? It's x minus x squared. So this gives us the f, which is the height. And then we put dx like this by the method of the cylindrical shells. Right, so which means the volume is the integral from 0 to 1, 2 pi x squared, 2 pi x cubed, dx, which is 2 pi x cubed out of 3, 2 pi x to the 4th out of 4. You plug in the 1, 2 pi out of 3, 2 pi out of 4. Okay, so yeah, you can do your addition. Right, if you do the addition, then you can make everything out of 12, multiply by 4, getting 8 pi out of 12, getting 6 pi out of 12, multiply by 3, and therefore 8 pi minus 6 pi is 2 pi out of 12, and 2 pi out of 12 is equal to what? It's exactly pi out of 6 units cubed. Okay, now we look at example 3. Example 3. All right, so use cylindrical shells to find the volume of the solid generated when the region R under the curve. Let's take this one. Check this one out. Okay, from 0 to 2, you have this one, which is y equals x squared. Right, from 0 to 2, which means that you have 0 to 4. Right, over the interval from 0 to 4, that is revolved about the line y equals minus 1. Right, remember, you need to use cylindrical shells to find the volume of the solid generated when the region R under the curve x squared over the interval 0 to 2. Right, so it's revolved about that particular axis there, 0 to 2, like this. You revolve it about the line y equals minus 1. Then the volume. But first, now, for us to actually be in a position to find the volume, it helps to actually be in a position to find the actual area. To find the actual area. So to find the volume, first we find the area. So the area. So the area would be, for example, what? Okay, first we need to take note of the fact that if this is revolved about the line y equals -1, whatever you're going to have is that, for instance, here you're going to have something like this. And then also, like here, you're going to have something like this. Okay, let them not be in contact with each other. Let them be separated. Let them be separated. Let them be separated. Now, which is the square root of y. Okay, let's write. Okay, we note that y equals x squared means that plus or minus the square root of y is equal to what? Is equal to x. Take a look. So that now, x is the square root of y. And then you have the x at this point is like the square root of y. X at this point is 2. So now, if we want to form a shell here, you therefore realize that this shell would have its own sort of height. So let us first note that. Right, at each y in the interval from 0 to y, therefore will be from 0 to 4, the cross-section of r parallel to the x-axis generates a cylindrical surface of height what? This cylindrical surface would be of height what? Right, so this cylindrical surface is going to be of height from the square root of y, which is the x value, to the x value there. So the height. The height is 2 minus the square root of y. That is the height. And then you multiply the height and the radius. What is the radius? So you need to find the height, and also you find the radius to use the method of cylindrical shells. What is the radius? So the radius, therefore, can be seen as the distance, for instance, between -1 and any y value. So the distance from here to the highest point. Okay, the distance from there to the highest point. Let's just do this in green. So the radius becomes y plus 1. Therefore, the area from 0 to 4. Okay, Yar, let's first do the area. Okay, just forgive me when you get disconnected because it's just the network, I think. It might just be the network, but this is recorded, so you'd get the recording. The recording is not going to have any issues. So the area, for instance, is going to be 2 pi. Then you take the radius, which is y plus 1. Then you take the height, which is 2 minus the square root of y. So this is going to be sort of the area. This is going to be sort of the area. So this area is done even in metric. It did not look very different, because in metric we say it is surface area. In metric we say it is surface area. I'm going to just write it down quickly. Right, in metric, we say it is surface area. Right, surface area, which is 2 pi r h. Okay, so it becomes the surface area of a circle that has been split open, such that here we have 2 pi r and then the height. So this is the method of the cylindrical shells. So a circle that is like a cylinder like this at school, its surface area becomes 2 pi RH if you open it to this, the height, and then this one becomes what you call the circumference of the circle, 2 pi radius. Now, at this point, you would then say the volume. Right, the volume V. Y would be the integral from 0 to 4. 2 pi. Y plus 1, 2 minus the square root of y. dy. So 2 pi. The integral from 0 to 4. 2y minus y to the power 3 over 2 plus 2 minus y to the power 1/2 dy. 2 pi. The integral of this is going to be exactly the same as what? It's going to be exactly 2y squared over 2, 2 out of 5, y to the 5 out of 2. 2y minus 2 out of 3, y to the 3 out of 2. Two pi. Yeah, is it 2 pi? Yes. And then 2. And this one is 2y squared over 2 is like y squared. Can write only y squared. Minus 2 out of 5. Y to the 5 out of 2. Plus 2y. Minus 2 out of 3. Y to the power 3 out of 2. From 0 to 4. The volume is 2 pi. Then you put the 4 squared. 2 out of 5, 4 to the 5 out of 2 plus 2 by 4. 2 out of 3, 4 to the power 3 out of 2 minus 0. Which is equal to 176 pi divided by 15. Okay, so this is exactly by the method of cylindrical shells. Right, this problem was solved before, but we used a different method. Right, we used the former method of the disc and washer, but here we are actually obviously, or we use what we call the washer method. All right, that's fine. We're concluding at exactly 7:20. Right, so let us move on. Okay, now, for example, here is the TART question, and let us discuss the TART, and then we're concluding at 7:20. Right, obtain the volume of the solid whose base is enclosed by the circle. Right, whose base is enclosed by the circle, x squared plus y squared equals 1, and whose cross sections perpendicular to the x-axis are semicircles. Right, so now let us do this question carefully. But we need to find the volume of a solid whose base is enclosed by the circle. Right, and and whose cross sections perpendicular to the x-axis are semicircles. Right, so we have exactly that. And this is exactly the XY plane. And we need to find exactly this volume of the solid, So if you look at this circle here, it is actually exactly the same as x squared plus y squared. That is the circle. And then you're looking at the semicircles. Right, and so if you're looking at the semicircles here, the semicircles are such that, and whose cross sections perpendicular to the x-axis. So now, if you are to look at this, for instance, and you look at the cross section, this is y and that is x. Right, the cross sections perpendicular to the x-axis are semicircles. Yeah, you have the semicircles there, perpendicular to the x-axis. The cross section becomes a semicircle. Right, 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 right. Okay, take a look at these and reason very, very carefully. On what axis is this sitting? Is it sitting on the x-axis? Is it sitting on the y-axis? The question is, I want us to be very careful here in terms of whether this is like this. Because now when the examiner says whose cross sections perpendicular to the x-axis, and this is the x-axis, and this is the y-axis, are semicircles. Can make sense that these things themselves, if this is the x-axis that you have here, and this is the y-axis, and these are perpendicular to each other, you can see that this appears to be actually sort of sitting, and these curves themselves appear to be sitting on the y-axis. Okay. And now you need to obtain the volume of the solid whose base, right, here's the description. The volume of a solid whose base is enclosed by this circle. Right, so now let us find the volume. So if we want to find this particular volume, you can use any of the method, but because this one is the base, it's the x-axis, or the base is actually the y-axis, and so we can decide to revolve it like so. Right, so if we decide to say we're going to revolve it very, very carefully, we're going to revolve it very, very carefully, like this. Right, if you revolve it that way, about the x-axis, what then do you have here? So now you're able to see that revolve it about the y-axis, what you're going to have what? So you're going to have disks. So what you're going to use, you can use the disk method, but you can also use the method of cylindrical shells. Right, let us use the disk method. So then using the disk method, you're going to actually be in a position to see that you're going to have exactly the following. Yeah, check. So the volume is going to be, for instance, if you revolve about the y-axis, you're going to therefore be in a position to have exactly the following. Or you use the method of cylindrical shell, doesn't really matter. Right, I'm going to use, I think, the method of the disk. Right, so if you use the disk method, you will therefore have to remember that what is the radius if this is revolved about this? So you have to actually look at the fact that you're going to have pi and what are you going to have is this particular function here. What are you going to have is this particular function here. You're not going to have exactly the following notion. You're going to have precisely the following notion. Okay, right. So what you're going to have is you're going to have uy. Okay, there are many methods. You can use any of the other methods. The answer must be the same. But now I think the one of the, because if you revolve this, it's going to actually, it's sitting exactly on the y-axis, so it's going to form a disk. Right, so you're going to use the uy, and then you square it. And then you're going to have dy. Right, and then you do c to d. And then you integrate. Right, so if you integrate these very carefully, then what are you going to have if you revolve these exactly about the y-axis? So the y-axis, therefore, is going to you're going to integrate from -1 to 1. And then pi, what is the y? Right, so this is x equal to, x is plus or minus the square root of 1 minus y squared. 1 minus y squared. Right, so you can actually take these as 1, either the plus or minus section, and then you square it. You square the plus or minus, y minus y squared. You square it dy, but obviously, yeah, it's positive this side, but you can also have it the other way. Right, so, which means that you'd have the integral from -1 to 1, pi, and then 1 minus y squared, dy. Which is y minus y cubed out of 3, pi. And then if you put 1 here, you would put 1 minus 1 out of 3. And 1 minus 1 out of 3 is actually 2 pi out of 3, which is exactly this. Okay, but now we use the method of the disks, okay? And then you can use also the method of the shells. But obviously, yeah, we conclude the discussion right now. It's 7:22. Thank you so much for joining us. Please advise me, what time can we meet later today? What time? Please check your program. Check your program and advise me what time we can meet later on today. Okay, now maybe like earlier afternoon, 2 p.m., 2 p.m. or 4 p.m. Please advise me. Please advise me.